Hello everyone and welcome again to CSEN701 Embedded Systems Architecture, also referred to as Real-Time Embedded Systems. Today we are going to discuss tutorial 3, which tackles the Atmel AVR Instruction Set Architecture, and we will be tackling the concepts of bitwise operations and bit masking, and finally we will end with an introduction about embedded C programming. Before I start, first of all, tutorial 3 will be given to all students on campus. Therefore, if you missed this tutorial on campus, you can watch the online video. And now let's start. And actually, let me recap what is the AVR Instruction Set Architecture. As you can see, we have a company called Atmel, which was brought later by Microchip Technology. Atmel designed an architecture called the AVR Instruction Set Architecture and produces a line of microcontrollers called the Atmega microcontrollers. We will be dealing with the Atmega 328P microcontroller, which is present on the Arduino Uno board. So actually we have the Arduino boards. There are different types of the Arduino boards. For example, you have the Arduino Uno, the Arduino Mega, the Arduino Deo, etc. The Arduino Uno board has the Atmega 328P microcontroller embedded on it, while for example the Arduino Mega has the Atmega 2560 microcontroller embedded on it. However, all of these microcontrollers follow the same architecture, which is the AVR Instruction Set Architecture, which is mainly an embedded architecture. First of all, if you remember from your computer architecture course, we have two main different types of architectures. We have a von Neumann architecture and we have a Harvard architecture. And as you can see, the AVR microcontrollers follow the Harvard architecture. So what is the difference? If you remember, the von Neumann architecture, we had the program and the data in the same physical memory. So we had one physical memory that contains the program or the instructions that I'm going to execute and contained the data. However, in a Harvard architecture, we have two separate physical memories. So the program will be in a memory and the data will be in a totally different memory. And here, the AVR Instruction Set Architecture is based on the Harvard architecture, which has two separate physical memories, one for the program or the instructions I'm going to execute, and the other is for the data. It is an 8-bit advanced RISC microcontroller. So actually, the width of our data is 8 bits. So we have registers. Each register width is 8 bits. So each register can have a value of 8 bits. Even the data stored in the data memory is 8 bits long. However, since we are based on the Harvard architecture, the 8-bit represents the size or the width of the data memory and the registers. However, the program's width is 16 bits or can be different. Here in the Atmega 328P, it is 16 bits, the program width, or an instruction is 16 bits long. Therefore, the program memory width is 16 bits. However, the data memory width is 8 bits and the registers will be 8 bits too. Moving on, it's an advanced RISC microcontroller. So actually, if you remember the difference between RISC and CISC, RISC is reduced instruction set computer and CISC is complex instruction set computer. And the difference is that the RISC instructions are simple and perform simple operations and take fewer clock cycles. However, CISC instructions are complex and perform complicated operations and takes more clock cycles, because actually one CISC instruction can perform multiple operations. So actually we need multiple clock cycles to perform all operations according to the CISC instruction. And actually a CISC instruction may correspond to a sequence of RISC instructions. I can have a CISC instruction, one instruction that performs addition followed by multiplication. However, in a RISC architecture, I need to have an addition instruction, and after I finish the addition instruction, I need to use a multiply instruction to perform the multiplication. Therefore, CISC architectures or CISC instructions take more clock cycles compared to RISC architectures. And since we are dealing with an embedded system or an embedded microcontroller, it is based on a RISC architecture, on a simple architecture, because as you remember, the characteristics of embedded systems, they are simple and perform simple tasks. So we do not need a complex architecture that takes multiple clock cycles. We only need a reduced or a simple architecture. Therefore, the AVR architecture is based on the RISC paradigm. Finally, it is a microcontroller, not a microprocessor. And if you remember the difference between microprocessors and microcontrollers, if I have a chip and this chip will be called a microprocessor if the entire chip is occupied by CPU and computing elements or computing components. However, to connect, or for example, if I want to connect a memory to a microprocessor, I need to connect it externally. I do not have a memory inside the chip of the microprocessor. I do not have I/O peripherals inside the chip of the microprocessor. However, in a microcontroller, I have one chip which contains the CPU, which has the ALU and the computation components, and I can have a memory inside the chip. I can have I/O peripherals inside the chip. I can have an Eep Rom, and we'll talk later about what is an Eep Rom inside a chip. Therefore, a microcontroller is connected internally with all of the other components. However, a microprocessor will be connected externally to the other components like the memory and I/O peripherals. And as you can see, a microprocessor will have more computing power compared to a microcontroller because the microprocessor chip is full of CPUs and ALUs, for example, while the microcontroller chip contains other elements. Therefore, the size and the number of components and the number of CPUs will be less. And definitely in an embedded system, we need less computation power, so we use microcontrollers. We do not use microprocessors. Also, because the space, we cannot actually externally connect other devices, or I mean connect other elements like the memories. So everything is on a chip, and it is called a microcontroller. Let's move on to the memory of the Avr Instruction Set Architecture. First of all, as I told you before, it is based on the Harvard, or actually to be more precise, the modified Harvard architecture. So we have a memory for the program and a memory for the data. Let's talk about the data. We have 32 general purpose registers called the GPRS from R0 to R31. And these general purpose registers are used to actually store intermediate results. If I'm performing an addition operation, I will store the result in one of the general purpose registers. Okay, so actually they just contain temporary values or intermediate results before storing them to the memory or the data memory. We have something called the I/O registers. And since we are dealing with a microcontroller or an embedded system, the I/O registers are a special type of registers which actually control the configuration of the microcontroller. So I am not using them to store intermediate or temp values. However, I am using them to actually control the settings of my microcontroller. For example, I can have a register that controls the analog to digital conversion mechanism. So if I want to enable the ADC, I need to set one of the bits inside the register, an I/O register, to 1. So each component and my microcontroller, or each operation in my microcontroller, is controlled by a set of I/O registers. For example, we have timers and counters. These have a set of registers that control the operations of the timers and the counters. We have the analog to digital conversion, which is controlled by a set of registers. We have interrupts, which is controlled by a set of registers. These registers are the I/O registers, and they are used to control the different operations inside a microcontroller, whether I want to enable or disable such operations, or actually the bits inside these registers convey me with some information regarding the operations occurring. So they may be, for example, like flags. If you remember the zero flag from the computer architecture course in the MIPS pipeline, or the MIPS pipeline data path, actually the zero flag was what was a bit, or was a flag that conveys to me that the arithmetic operation result was 0. So I was checking on this flag. Here in our AVR architecture, the 0 flag will be a bit inside one of the I/O registers. So if I want to know the value of the 0 flag, I'm going to retrieve or read this bit from a particular register. Followed on, we have the SRAM, or the static RAM, which is the normal data memory. Okay, so actually the stack, for example, if I want to store data using the stack, I can use it in the SRAM. If I want to store data in general using load and store, I'm going to store it or load it from the SRAM. Now let's move on to the program memory. As I told you before, the data memory is 8 bits long. Okay, so its width is 8 bits. It actually stores 8-bit data. Even the data memory and the registers all store 8-bit data. However, here in the program memory, we have a totally separate memory, which is a non-volatile memory. Take care, the data memory is volatile. If I unplug my microcontroller, everything in the data memory will be gone. However, the program memory is not volatile, is non-volatile, meaning if I unplug my microcontroller and plug it again, it will perform the same set of instructions that were present inside the program memory. Okay, so the program memory is separate from the data memory, and it is a non-volatile memory, so it stores the program even if I unplug my microcontroller. And here in the Atmega 328P, the length of one instruction is 16 bits. Therefore, the program memory is divided into 16 bits words. So one word is 16 bits here for the program memory. However, in the data memory, one word is 8 bits, because actually one line in the data memory stores 8 bits. One line in the program memory stores 16 bits. And take care. Finally, we have the Eep Rom, the electrically erasable programmable read-only memory. Okay, this is a third type of memory that is actually present in our microcontroller, and this memory is a non-volatile memory. So if I unplug my microcontroller, the data stored on the Eep Rom will not be erased or will not be gone, and you can actually program it or write to it multiple times, and you can read from it. And it is used to actually store the configurations or the settings of the microcontroller. Or if you want to store permanent data, or if you want to store some data that you do not want to lose after unplugging your microcontroller, you will store it on the Eep Rom. Because as I told you, the SRAM or the data memory is volatile. If you unplug it, everything will be gone. However, in the Eep Rom, it is not volatile. So you can actually store important data that you want to actually retrieve even if you unplug your microcontroller inside the Eep Rom. So as you can see the memory hierarchy, we have the data memory, which consists of the general purpose registers, the IO registers, and the SRAM. It's a volatile memory. We have the program memory, which contains my programs, instructions I want to execute, which is a non-volatile memory. And finally, we have the EEPROM, which actually stores configurations of the microcontroller or data that I want to retrieve even if I unplug my microcontroller later on, which is also a non-volatile memory. Now let's start with our first question, and what does the SRAG in Atmega contain and when is it updated? So SRAG stands for Status Register, and it contains information about the result of the most recently executed arithmetic instruction. It is updated after all ALU operations. So as you can see, the status register is not a general purpose register, meaning that it is used to actually control the functionalities of my microcontroller, or it will actually notify me with some information about the operations occurring inside my microcontroller. It's an 8-bit register, as you can see from the figure, and actually here each bit inside this register is related to a specific operation that is occurring inside my microcontroller. However, the SRAG is mainly related to arithmetic operations, and it is updated after each and every arithmetic operation. So I performed an arithmetic operation inside the ALU. After it, the SRAG or the status register will be updated. So it is updated after each and every arithmetic operation. And it will actually tell me information about the recently executed arithmetic operation. And we will see what are the different bits present inside the status register. So the second part of the question explains the different bits of the status register. As you can see, it's an 8-bit register from bit 0 to bit 7. And here, each bit is actually notifying me or telling me information about the operation or the arithmetic operation that just occurred in the ALU, or the last arithmetic operation that occurred in the ALU. However, we will only need 6 out of the 8 bits to inform me about the result or information about the last arithmetic operation. So bits from 0 to 5, which are 6 bits, are the only bits inside the status register that are related to the arithmetic operation that occurred inside the ALU. However, bit 6 and bit 7, which are the T and I bits, are not related to arithmetic operations, and they were inserted into this register because the designers of the architecture did not find any other free register to insert these 2 bits in, and they found out that they only need 6 bits to represent information about the last arithmetic operation, and there are 2 empty bits, so they actually inserted a bit called the T bit and a bit called the I bit, which we'll explain later in the next slides. into the status register. So let's start from the end and let's talk about the most significant bit, which is bit number 7. Bit 7, which is the I bit, is called the global interrupt enable. And from its name, you can see that it is not related to an arithmetic operation. It tackles interrupts. The I bit can also be set and cleared by the application with the set interrupt, which is SEI, and the clear interrupt, which is CLI instructions, as described in the instruction set reference. So before we explain what is the global interrupt enable, there are two assembly instructions, set interrupt and clear interrupt, that actually directly operate on bit number 7 in the status register. Okay, so actually set interrupt will change the value of bit number 7 in the status register to 1. Clear interrupt will directly change the value of bit number 7 inside the status register into 0. So we have two assembly instructions that directly operate on bit number 7 of the status register. So we'll see that it is a really important bit and it is not related actually to any arithmetic operation. The global interrupt enable bit must be set for the interrupts to be enabled. The individual interrupt enable control is then performed in separate control registers. So actually, if you know the concept of interrupts, if I am executing my program or a list of instructions, I may be interrupted, okay? An interrupt means that it will stop performing what it is performing, it will go execute another function or method, and it will return back to continue my old program. So actually I'm executing a program, an interrupt occurred. So actually it will stop executing this program, it will remember when it left this program, it will go execute a separate function or method, and then it will return to continue executing my old program. Okay, this is the concept of interrupt. So actually to enable this concept in the microcontroller, we have a master switch called the global interrupt enable. And this master switch, if it is turned on, and turned on meaning I put 1 in bit number 7 in the status register, setting this bit to 1 will enable the master switch or the global interrupt enable, and therefore all interrupts can actually work. However, this is just a master switch to enable the concept of interrupts. But in my microcontroller, I have different types of interrupts. For example, I have an ADC interrupt, meaning that if I was performing an analog to digital conversion in the background, and actually it finished, it will interrupt my program and notify me that the ADC conversion has finished, and do whatever you want to do with the result of the ADC, and return back to my program after the interrupt finishes. I can have, for example, interrupts regarding the environment. If I'm sensing or waiting for data from the environment with a sensor, and this data, for example, if I clicked on a button, I want to interrupt my program and perform another functionality. I can have an interrupt that detects if I click on the button or not. We have multiple interrupts, and each actually interrupt has its own control registers. So for example, if I want to enable the ADC interrupt, which informs me that the ADC operation has finished, I need to enable the local ADC interrupt in a specific ADC register. Okay, so actually in order for this ADC interrupt to work, I need to enable the global interrupt enable in the status register, bit number 7 in the SRAG, and also I need to enable the local interrupt for the ADC. Even if I enabled the local interrupt for the ADC and I did not enable the global interrupt, it will not work. So for the local interrupts to actually work, the master switch or the global interrupt must be on, and then I, as a developer or as a programmer, will choose the specific or local interrupts that I want to turn on so they can trigger an interrupt. So actually to turn on an interrupt, I need to perform two steps: enable the global interrupt enable, and then enable the local interrupt, whatever type of interrupt I want to perform in their specific register. Let's move on. If the global interrupt enable register is cleared, none of the interrupts are enabled independent of the individual interrupt enable setting. So actually this was what I was telling you. Even if I actually enabled an individual interrupt, if the global interrupt is not set, if it was cleared, it will not work. Okay, the local interrupt or the individual interrupt will not work unless the global interrupt enable is set. And when I say set, means the bit is 1. When I say clear, means the bit is 0. Finally, the I bit is cleared by hardware after an interrupt has occurred. and is set by the RETI, which is the return interrupt instruction. It's an assembly instruction to enable subsequent interrupts. So actually, a rule of thumb, an interrupt cannot interrupt an interrupt. So multiple interrupts are said. Okay. So actually, if I was executing my program and I have two interrupts, interrupt X and Y, which can be triggered, I actually enabled the global interrupt enable, and I enabled the local interrupt for interrupt X and interrupt Y in their respective registers, and I was executing my normal program, and then interrupt X was triggered. So what will happen? My microcontroller will stop executing the program it was executing and will then go to perform or operate on a certain method or function and return back. While it is operating on a specific method or function of interrupt X, interrupt Y cannot interrupt the functionality or operation of interrupt X. Interrupts can only interrupt the main program. They cannot interrupt each other. I cannot have an interrupt interrupting another interrupt. Okay, so actually, how can I prevent this? Automatically, when an interrupt is triggered, the global interrupt enabled by the hardware, by the microcontroller, will be cleared automatically. Cleared meaning what? It will be 0. Therefore, no other interrupt can work, because to be triggered, you need to have the global interrupt enabled set to 1. And then, after my triggered interrupt finishes executing whatever it is executing, the function or method, and returns back to the main program, the global interrupt enable will be set back again to 1, and then interrupt Y can trigger or interrupt my main program later on. Okay, so actually interrupts cannot interrupt each other. They can only interrupt the main program, and that's it. Now let's move on to the next bit, which is bit number 6, the T bit. Okay, it's also known as the bit copy storage bit. The bit copy instructions BLD, which is bit load, and BST, which is bit store, they are assembly instructions, use the T bit as source or destination for the operated bit. So actually, they are used for storing temporary bits. If I want, for example, I'm performing an operation and I want to store a bit temporary in a location, I have two direct assembly instructions that operate on bit number 6 in the status register, which is the T bit. Okay, T from temporary. I can store or load directly from this location in the SREG, bit number 6 in the SREG. Instead of performing complex operations to store in other registers, if I want to store a bit, and for example, if you remember in Java, if I want to swap two values, I had to create a temporary variable to store one of the values while I'm performing the swapping. Here it is the same scenario. The T bit is like a temporary location. You have direct access to it using two instructions. The designers of our architecture created two instructions to directly access bit number 6 in the SREG. Okay, so I can store and load directly from it bits if I'm performing temporary operations like swapping. Okay, a bit from a register in the register file can be copied into T by the BST, which is bit store instruction, and a bit in T can be copied into a bit in a register in the register file by the BLD instruction. So the BST stores into location bit number 6 in the SREG. BLD will retrieve bit number 6 in the SREG and actually put it to a register, or put this bit in a corresponding register. Okay, and as you can see, bit number 7, the global interrupt enable, and bit number 6, the temporary bit, these are not related to any arithmetic operation. So actually they were present in the status register because the designers cannot or did not find a free register to put these two bits in. Therefore, they put them in the SREG or the status register. Now let's move on to the arithmetic bits. And the first bit is bit number 5, which is called the half carry flag. The half carry flag H indicates a half carry in some arithmetic operations. Moreover, half carry is useful in arithmetic, which is the carry from bit 3 to bit 4. So now let's have a live demonstration or illustration. If we move on here, and just let's have an example. We can increase the font. Okay, if I'm having this instruction 0001, as I told you, all our values are 8 bits. So actually I will be dealing with 8-bit addition operations, subtraction operation, etc. Okay, and let's here have, for example, 1 0 0 0, and if I do like this, okay, I took 1 0, so 1 2 3 4 5 6 7 8, and I want to perform an addition operation. Okay, so we have this value, and if I set, okay, so actually we want to determine the result of this operation. If I want to perform the addition operation, 0 plus 0 will be 0, 0 plus 0 will be 0, 0 plus 0 will be 0. It's very hard to write actually in using this. 1 plus 1 is actually what? 0 and what? Carry 1. Okay, so we have here, let me just write it better. We have here carry 1. Okay, 1 plus 1 is 0, carry 1. So actually this is bit number 0, this is bit number 1, this is bit number 2, this is bit number 3, and this is bit number 4. So as if I just divided this. This is bit number 3 and this is bit number 4. Okay, the carry from bit 3 to 4, which is this one, will be stored in bit number 5 in the status register, which is the half carry bit. So actually, as I have in this example, if I'm having a carry from bit 3 to bit 4, this carry or this value will be stored in the half carry flag. Okay, therefore the half carry flag will have in this case 1, because 1 plus 1 is 0, carry 1. So this one will be stored in bit number 5 in the status register, which is the half carry flag. So if we move on to our slides, this is the half carry flag. Now we have the 2's complement overflow flag. This flag is set whenever the result of a signed number operation is too large, causing the high order bit to overflow into the signed bit. Take care, we skipped actually bit number 4, which is the signed bit. We'll be talking about it later on. I need to first explain the overflow and the negative bits, and then I will return to the S or signed bit. So let me explain bit number 3, which is the overflow bit. And by the way, overflow occurs only in signed operations. I cannot have an overflow in an unsigned operations, because the problem of overflow or the problem of signed operation is that signed operations is that I cannot represent the signed bit. Okay, I do not have a location, or actually if my result is 8 bits, the signed bit cannot be properly represented in 8 bits. I need one more bit to represent the signed bit. This is overflow. Therefore, it only occurs in signed operations. And take care, an overflow does not mean having a carry at the end of signed operations. So actually, if the last carry is 1, this does not mean that we have an overflow. I can have actually an overflow and the last carry is 0, because a lot of people get confused about carries and overflow. An overflow occurs in signed operations, and even if the last carry is 1, it does not mean that we have an overflow. And here we have a simple hack. How actually to determine if we have an overflow or not. Normally an overflow occurs, for example, if I'm adding 2 positive numbers and I found my result is negative. Or if I'm adding, for example, 2 negative numbers and I found my result is positive. Meaning that, how do you know the sign of a number or the sign of my result? The most significant bit, bit number 7, represents the sign bit in signed numbers. So if bit number 7 is 1, it means the number is negative. Bit number 7 is 0, means the number is positive. Therefore, if I am performing an addition of 2 numbers of 2 positive numbers and I found that the result bit number 7, the most significant bit, is 1, this means that an overflow occurred, because adding 2 positive numbers should result in what? In a positive number. Okay, adding 2 positive numbers will result in a positive number, not a negative number. So we have this quick hack. XOR the last 2 carries, the carry from bit 6 to bit 7 and the carry from bit 7 to the air, or to the imaginary bit 8, which does not occur. Okay, if XORing the last 2 carries resulted in 1, this means we have an overflow and it will be stored in the overflow bit. However, if the result is 0, it means that we do not have any overflow. And let's have a quick example. So now let's have a quick example regarding the overflow flag. Here, let me give you a simple example. If we have 1,0,0,0,0,0,0, which is negative 128 plus 1,0,0,0,0,0,0. So I'm trying to add negative 128 to negative 128. The expected result should be negative. And I can increase the font. Why it's not increasing? Oh, yeah. Okay. Now let's perform what? The addition operation. Okay. 0 plus 0 will be 0. 0 plus 0 will be 0. 0 plus 0 will be 0. And finally, 0 plus 0 will be 0. The second half, 0 plus 0 is 0. Here is another 0. A third 0. 1 plus 1 is what? 0 carry 1. Okay. This one is called the carry bit. It is not the overflow bit. Having 1 at the end does not mean we have an overflow. Okay, I repeat it because it is very important. Having 1 at the end means we have a carry, and carry is actually important to unsigned numbers. To signed numbers, we do not care about the carry. However, our microcontroller is not smart enough to actually know whether we are performing a signed or an unsigned operation. It is just performing calculations on bits. Therefore, it is the role of the programmer to know what type of operation they are performing, a signed or an unsigned operation. However, both the overflow flag and the carry flag, which we'll talk about later, will be updated after every arithmetic operation, regardless whether it is signed or unsigned. So here we have a carry flag, and the carry flag will be 1. Even if this is a signed operation and we do not need the carry flag will be set by 1. However, the programmer will discard this value or will not actually check on the carry flag. Here, as I told you, the simple hack of knowing whether we have an overflow or not. By your eyes, you can see I'm adding negative number to a negative number, and the result is positive. Okay, negative 1 to 8 plus negative 1 to 8, I should have a negative number. However, the result is 0, which means that we have an overflow. If we perform actually the hack, which is XORing or XORing the last two carries, the last carry is 1, and the carry before the last is 0 plus 0 is actually 0, carry 0. So the last two carries are 1 and 0. 1 XOR with 0 will result in 1. If you remember the XOR table, 0 XORed with 0 is 0. 0 XORed with 1 is 1. 1 XORed with 0 is 1. 1 XORed with 1 is 0. Therefore, 1 XOR with 0 will be 1, and the over flag will be set to 1. Let's move on to another example. If we just delete all of this, and let's have another example. 0, 1, 0, 0, 0, 0, 0, 0. This is 64 plus 1, 1, 0, 0, 0, 0, 0, 0. This is negative 64. Okay, so actually 64 plus negative 64 should result in what? Should result in a 0. Okay, let's have the operation, or let's perform the operation. Here we have 4 zeros added together, so it will be 4 zeros. By the way, you can use your calculator during your exam to do the conversion from decimal to binary and from binary to decimal. And then when we will introduce hexadecimals, you'll also use your calculator to actually convert to hexadecimal or from or to hexadecimal. Here, 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 1 is 0. Carry 1. And what? 1 plus 1 is what? 0. Carry 1. Okay, as you can see, 64 plus negative 64, it resulted in zeros. Okay, this is perfect because this is actually the answer. However, at the end we have what? We have a carry. Is this carry an overflow bit? As I told you, no, it is never an overflow bit. It is only a carry bit. If we perform our hack, checking the XOR or XORing the last two carries, 1 XORed with 1 results in a 0. Therefore, the overflow flag will be 0. Because as you can see, 64 plus negative 64 should be 0, and the result is actually 0. Where is the overflow flag? The operation was actually performed correctly. Therefore, no overflow occurred, and the overflow flag will be 0. And according to our hack, 1 XORed with 1 is actually 0. And this worked perfectly. Even if I had a carry bit at the end, yes, the carry flag will be set to 1, but I don't care about the carry flag. I only care about what? The XORing the last two carries to determine the overflow flag. Now let's have our last example regarding overflows. If we just erase everything here. Okay, let's have our beloved number 64, 01000000 plus 01000000. I'm adding two positive numbers and the result should be positive, and both positive numbers are 64. Okay, let's do it like this. Okay, let's perform the arithmetic operation. 0 plus 0 is 0, 0, 0, and 0. 0 plus 0 is 0, 0 plus 0 is 0, 1 plus 1 is 0, carry 1, and 1 plus 0 is 1, carry 0. As you can see here, we added two positive numbers. However, the result is a negative number. The most significant bit, bit number 7, which should represent the sign, is 1, which means it is negative. Therefore, we definitely have an overflow. If we use our simple hack to check or to XOR the last two carries, 0 XORed with 1 will result in a 1. Therefore, the overflow flag should be set to 1. However, as you can see, the last carry is 0. Okay, this is 0. But guess what? We have an overflow. As I told you, the carry bit is not related to the overflow. Having a 1 or a 0 at the end does not determine whether we have an overflow or not. Okay, so actually I showed you all examples on how to determine the overflow flag. If we erase all of this and move back into our slides, tutorial slides. Yeah, let's move on to bit number 2, which is the negative flag. The negative flag N indicates a negative result in an arithmetic or logic operation. It is very simple. The negative flag, which is bit number 2, it takes the most significant bit, bit number 7, from the result and put it in the N flag. So actually, if the most significant bit is 1, bit number 7 is 1, the N flag will be 1, indicating that the result is a negative result. However, if the most significant bit, bit number 7, is a 0, which is a positive number, the N flag will be 0, indicating that the number is positive. And this is used to know the actual result, okay, the result that was output to me as a programmer, whether it is a positive or a negative. So if I have, let's move back to our drawer. If we had this example, 0, 0, 1, 0, 0, 0, 0, 0, and here let's have, for example, 1, 0, 0, 0, 0, 0, 0, 0. Okay, as you can see, the result, bit number 7 of the result will be what? Let me just click on this. Okay, this will be 0, 0, 0, and 0, then 0, 1, 0, and 1. The most significant bit is 1. Okay, bit number 7 is 1, indicating that this number is a negative number. I do not care about the assumption or actually what is supposed to be. Okay, I just care about the actual result in front of me, in front of my eyes. The most significant bit is 1, therefore the N flag will be 1, indicating that this number is a negative number. If it is 0, it will indicate that it is a positive number. And it is very simple. Let's go back to our slides. Okay, and let's move on to the sign bit. So actually we knew that bit number 3 is overflow bit and bit number 2 is the N bit. We're going to return to bit number 4, which is the sign bit, because actually the sign bit should represent the expected sign of a number. So if I'm actually, remember from the overflow examples, I am adding two positive numbers, however, the result was a negative number. The sign bit represents the expected sign of the number, not the actual sign. The actual sign is represented in the N flag. However, the S bit or the S flag represents the expected sign. I am adding two negative numbers and the result should be negative. Okay, this is the expected sign. However, the N flag will tell you the actual result that occurred. It is the XORing of the negative flag and the overflow flag. The S bit is always an exclusive OR between the negative flag and the overflow flag. Bit set if answer is negative with no errors, or if both numbers were negative and an error occurred, 0 otherwise. So actually, just let's draw the truth table. If we go back to our drawer, well, yeah, okay. No, I do not want, no, okay. So we have here, for example, the N. Yeah, it's a huge N. We have here the V, and we have here the S. Okay, and we can draw a line here, and we can draw a line here. Okay, it's a very bad line, but you guys gonna manage it and cope with it. Okay, we have here 0, 0 will result in what? 0. 0, 1 will result in a 1. 1, 0 will result in also a 1. And finally, 1, 1 will result in what? A 0. And this is what? The exclusive OR. Okay, it is XOR. Can write it here, XOR. Okay, so let's actually understand why the sign bit is the exclusive OR of the negative flag and the overflow flag. And as I told you, the sign bit represents the expected sign of the output, not the actual sign. The actual sign is represented through the N bit. So the N bit is 0, meaning that the number is positive. And actually, the overflow flag is 0, indicating we did not have an overflow. Therefore, what? The sign should have been what? Should have been positive, because the actual sign is 0 and I do not have an overflow. Therefore, the sign should be positive, which is correct. Here, the N bit is 0, indicating a positive number. However, the overflow flag is 1, indicating that what? The sign of the output is wrong. It should be the opposite. So if the sign was here from the N was 0 and I have an overflow, this means that the sign should have been 1, should have been a negative number. Therefore, what? The sign bit is what? Is 1. Okay, as you can see, N means 0, means the actual output sign is 0, it's positive. However, the overflow flag is 1, indicating what? That an overflow occurred and this sign is wrong. Which sign? The N bit. Therefore, I complement the N bit and it will be 1. So the expected sign of the result is 1. Here, the N bit is 1, indicating the actual result is a negative number. However, the overflow flag is 0, indicating we did not have any overflow. Therefore, what? The expected sign will also be what? Negative. Finally, the negative flag is 1, indicating that the actual result is a negative number. The overflow flag is 1, indicating that what? That the sign is represented in a wrong manner. Okay, this is not the correct sign. This 1 should have been a 0. Okay, it's not a negative number. The result should have been a positive number. Therefore, what? The sign bit is what? Is 0. So here, the actual sign was 1. However, I had an overflow, meaning that the sign should have been a 0. The overflow means that the sign is wrong, whether it is 1 or 0. Having 1 in the overflow, I repeat, having 1 in the overflow does not mean that it should have been a negative number. No. Here, the number is a negative number, but having 1 in the overflow means that it should have been a positive number. And therefore, the sign bit will be 0, and this operation is the exclusive OR of the negative flag and the overflow flag. Now we are done with the sign bit, and that's why I kept it to the end, because we had to understand the negative and overflow flag bits at first. Let's move back to our slides. Okay, we have here bit 0, then we'll return to bit 1, but no, let's start with bit 1 first. Bit 1 is the 0 flag, okay? And it is exactly the same concept of the 0 flag in the MIPS processor. The 0 flag indicates a 0 result in an arithmetic or logic operation. So actually, if my result or the result was a 0, this means what? That the 0 flag will be 1. If the result was any other number other than 8 zeros, this means that the 0 flag is 0 and the result is not a 0. It is the same exact concept of the MIPS 0 flag or that flag. If my arithmetic operation resulted in value 0, which is in binary 8 zeros, the 0 flag will be 1. However, if it resulted in any other values, at least one of the 8 bits is 1, then the 0 flag will be 0. And we can actually have an example. I know it's very simple. For example, if I'm doing this, 0100, 0100, and here plus 11000000. The same exact example of 64 and negative 64. And we click OK. We click on this and here. Well, here will result in 4 zeros. And here we'll have 0, 0, 1 plus 1, 0, carry 1. 1 plus 1 is what? 0, carry 1. So here my result is what? Is 8 zeros. It's a 0. So the Z flag will be equal to 1. Otherwise, if one of these 8 bits were at least 1, the Z flag will be 0. And now let's go back to our flags and the last flag, which is the carry flag. This flag is set whenever there is a carry out from bit 7. This flag bit is affected after an 8-bit addition or subtraction. So actually carry is important to unsigned numbers, not to signed numbers, as I told you before when I was describing the overflow flag. However, as I told you, my microcontroller or the microcontroller does not differentiate between signed and unsigned operations, because it is the programmer's intention whether this number is a signed operation or not. Therefore, the carry flag, if I have a carry from bit 7, the carry flag will be set. And we can have a quick example. Here, if we just undo all of this. Okay, it is very simple. We can have these two numbers. Okay, and we can actually increase its font to anything and click on the layer. And then, okay, 0 plus 0 will always result in a 0. So all of these are zeros. 1 plus 1 is what? 0, carry 1. Okay, this one will be stored in the carry flag or the C flag. So actually, regardless of it is being signed or unsigned, although carry is only useful for signed operations, this one will be stored in the carry flag or the C flag. Now we are done with our status register and the first part of the tutorial, which actually tackled the Avr Instruction Set Architecture. Let's move on to the second part of the tutorial, which tackles the bitwise operations and the bit masking. So, bitwise operations like the AND, the OR, the XOR, and the NOT are often used for bit fiddling. And bit fiddling is the change of the value of a bit in a register without affecting the other bits. So if I want to isolate a certain bit from the rest of the bits, I use bit fiddling techniques or bit masking techniques, which uses bitwise operations. Here, determine appropriate constant bit patterns called the masks that will change some bits while leaving others unchanged. Masks can be written in binary, hexadecimal, or even decimal, but usually we write it in hexadecimal. However, in the exam, if it is not stated which notation or which representation, hexadecimal, decimal, or binary, you can write it as you like. However, if it is specified in the exam, you need to actually follow the question and its rules. Let's consider an 8-bit variable called var. So actually we'll be dealing with some high-level language programming, and we have a variable called var or v. Sometimes we'll just call it v. And let's see our first question in the second part. What does the following operation do? I have here var equal var x ORed, with 0x80. Let me tell you something very important before actually solving this question, because a lot of your colleagues last year failed to realize so. The important remark is, if I want to write a hexadecimal number, I need to actually state before writing the number, or I need to write what? 0x and then the number. Okay, 0x means this number is represented in the hexadecimal representation. However, if I want to write a binary number, and actually people used to actually represent hexadecimal with 0x, however, people fail to realize that to represent a binary number, you need to write before it 0b and then the number. Okay, if you did not write 0b in your exam, you will lose marks, because actually the examiner will not know whether this number is a hexa, is binary, or is decimal. Okay, so if I want to write 5 in binary, it will be 1 0 1. Okay, if I did not write 0b before 101, I may read it 101. Who knows? So you need to specify whether this is binary or decimal. If I want to write a decimal number, I will just write 1 0 1 without anything before it. However, if I want to write a binary number, I need to write 0b before it. And if I want to write a hexadecimal number, I need to write 0x before it. And take care, each hexadecimal digit represents 4 bits. So example, if I write 0x 1 0, this means that it is 0b, it is equivalent to 0b 0 0 0 1, which is the first one, and then this 0 is represented in 4 zeros, 0 0 0 0. Okay, our last digit is f. F represents 4 ones. So if I say 0x f f, this means what? It is equivalent to 0b 1 1 1 1, and then the second f 1 1 1 and 1. Okay, so each hexadecimal digit represents 4 bits in binary, because you will guys use it in the conversions, and as I told you before, you will be using your calculator if you actually do not know how to convert manually. No problem in using your calculators during the exam. So if we just remove or delete everything we wrote, because we'll use this sketch for our questions. And why it is not deleting? It looks like I need to use an eraser. Or actually, if I can just select and delete. This is much easier. Okay, let's move on to our questions again. We have this, our variable var equal var ORed with 0x80. So let's just write it here. Var equal var ORed with 0x80, just to remember. Okay, so let's assume we do not know the value of var. Okay, var is an 8-bit variable, so actually just let's represent its values with x's. So we have 8 x's, meaning that I do not know its value. Okay, actually it could be anything. I'm just representing it with x. X is not don't care. Okay, because some of you may actually say that x is don't care. No, x here in this example, when I'm trying to illustrate, just means that I do not know the value for now, which actually may be represented in microcontrollers with another variable like z. But however, this is just simple. It is not related to microcontrollers. It is not related to computer architecture in embedded systems. For me now, x is just means I do not know the value for now. Okay, because some people will get confused and tell me axis don't care and z is the high impedance state, etc., etc. I'm not talking about this in this tutorial. I'm just stating that x for me is a number that I do not know. So I give it x. I could give it a, I could give it b, I could say c. However, I chose x. Okay? And then 0x80, 8 is 1, 0, 0, 0, and 0 is definitely 4 zeros. And what operation I'm trying to perform is OR. Anything ORed with a 0 will result in itself. So here I will have my x's again. Okay? However, anything ORed with 1 will result in what? In a 1. So this will be 1. So actually, what I'm trying to perform here, I am trying to set the most significant bit, bit number 7, to 1. So this operation sets the most significant bit to what? To 1. If you go back, we'll find that set the most significant bit to 1 without affecting the other bits, because actually what? ORing anything with 0 will result in itself again. So I'm not actually changing the bits. However, I am setting one bit, which is the most significant bit, to 1 by ORing it with 1 and 6 or 1 and 7 zeros. Now let's move on to the second question. Clear the least significant bit in var, which is set to 0 without affecting the other bits. When I say clear, it means changing the value to 0. When I say set, it means making it or setting it to 1 or changing it to 1. Over this just setting to 0, just to tell you that clear means changing the bit to 0. However, when I say set a bit, it means changing it to 1. When I say clear a bit, it means changing it to 0. Now let's move back to our sketcher or our sketch notepad. And if we delete all of this, okay, and we go back into, we do not want this layer anymore. Okay, and yeah, I want to delete this too. Okay, let's start. I can actually create a new layer. Okay, so here I have my variable, which is axis, because I do not know its value. So I have var, which contains 8 axes to me. And actually, I want to clear the least significant bit. I want this bit to be what? I want it to be a 0. Also, I need to actually, okay. I want it to be a 0. Okay. Which operation can I use to clear the least significant bit? As you all guessed, I will be using an AND operation. Okay. So I will AND. If I don't want to affect the other bits, I will AND with what? I will AND with 1. Because anything ANDed with 1 will result in what? In itself. So here I will have ANDed with 1s. And here I will have what? ANDed with 0. Because anything ANDed with 0 will result in a 0. Therefore, X ANDed with 0 will be 0. And the rest will be what? Will be X. Whether X is a 1 or a 0, I do not know. So ending with 1 will not affect the value of X. However, ending with 0 will force that the result will be 0. So actually this will be represented as, we have here 4 1s, which in hexadecimal will be an F, and 1110, which is, so I'm missing 1. 1, 2, 3, 4, 5, 6, 7. Yeah, I missed a bit at the beginning. Here it is an X, and here it is a 1, and here it is an X. So actually here is F, and here is E. So it will be 0xFE. If we move back, using an AND mask, which will be var equal var ANDed with 0xFE. However, there is a different solution. As you will see, I can use a not AND mask or an AND not hex mask, which will be var equal var ANDed with what? The negation or nothing the 0x01. What did we do here? If we go back to our sketch, instead of ANDing with 1, 1, 1, 1, 1, 1, 1, 0, I can AND with the negation, and this is the sign of the negation, with what? 0, 0, 0, 0, which will result in a 0 in hexadecimal, and 0, 0, 0, 1, which will result in 1 in hexadecimal. Okay, so actually not this number will result in what? 0 negated will be 1, 1, 1, 1, 1, 1, 1, and 0. So actually I could have an AND not mask, so I need to flip the bits, and therefore I flipped my mask, and then I said AND not the flip or the flipped mask. Okay, both are equivalent. You can even write the number in a binary representation using 0B11111110 if you want to. Okay, as you like. If it is not stated in the question, feel free to use anything you want. Let's move on to the next question. Flip the least significant 4 bits without affecting the other bits. So actually, if I want to clear, I use an AND mask. If I want to set, I use an OR mask. If I want to flip, which type of mask should I use? I will be using the XOR mask. And as I told you, if you recall the XOR table, if I just delete all of this. Okay, if you remember the XOR table, no, I need this. Okay. 0, 0 will result in a 0, 0, 1 will result in a 1, 1, 0 will result in a 1, and 1, 1 will result in a 0, and this is what the XOR mask. Okay, so which value should I XOR with to flip a bit? I mean, if I XORed 0 with 0, it resulted in a 0. No flipping occurred. However, if I XORed 0 with a 1, this 0 was flipped and became a 1. And here, if I XORed 1 with a 1, this 1 was flipped and became a 0. So actually, to flip a number, I need to XOR it with 1 to perform an exclusive OR with 1. And as you can see, we will use this mask. So if I have my 8 axes, and here we have, I want to actually flip the least significant 4 bits from 0 to 3, which are these 4 bits. So I'm going to what? To XOR. If I don't want to change the value, I will put zeros. Zeros will not change the value or flip the value. If I want to flip the value, I will XOR with ones. Okay, so actually here the values will be x's because x XORed with 0 will result in x itself. However, x XORed with 1 will result in x not. Okay, x negated. So this is x negated because actually I do not know the value of x, so I will just say x negated. Okay, 4 zeros is 0, 4 ones is f, so in hexadecimal it is 0x 0f, or in binary 0b 0000 1111. Okay, and this is, by the way, the sign of the XOR. Okay, so I could actually write it like this. I can say like this, and this represents XOR in embedded C programming, or when you program using your laptop or PC. If you want to actually perform an XOR operation, you use this symbol. Let's move back. And our next question, set bit 0 of var to a 1. So actually I want to set the least significant bit number 0 to 1. And as you know, setting a bit to 1 means what? I need to OR this specific bit with a 1, and the rest will be ORed with zeros. So actually if I delete my sketch, and I cancel this and I click here, so actually I have my 8 axes. Actually, I will be using an OR operation, and I want actually to set the least significant bit number 0 to 1. So I'm going to OR with all zeros, except the least significant bit will be ORed with a 1. So this will result in what? In x's. I'm not affecting, by the way, the other bits. All other bits remain unaffected, and that's the embedded C programming concept. As I told you before, if you remember from the microcontrollers, when I described microcontrollers, I told you that the I/O registers, for example, each bit is responsible for the operation of a certain component in the microcontroller. So if I want to enable the I bit, for example, in the SREG, I need to actually set this bit to 1 without changing the values of the rest of the bits, because each of the other bits have a certain role or a certain purpose. So we use what? In high-level programming, not assembly programming, we use the bit masks. Here, as you can see, this bit is set to 1. After what? After ORing it with 0000 0001, which will be 0x01. So if we go back, we will find that var equal var ort with 0x01. Let's move on to the next part. Clear the 4 upper bits in var. So clearing means that I will perform an AND operation, and I will the part that I want to clear, I will AND it with 0, and the other bits will be ANDed with 1, just to prevent the other bits from changing or affecting the other bits. So let's try this also on the sketch. Well, this time I'll be smarter and I will just delete the second part of my solution. And yeah, we can delete this X. Okay, and I can add here another X. So actually the 4 upper bits are these bits. So I want to clear them. I will AND them with zeros. And then I will AND the rest with ones. So anything ended with 0 will be 0, 0, 0, 0. Anything ended with 1 will be as it is, X, 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 and final X. So this will be the mask 0x 0f. 4 zeros is 0, and 4 ones is f, or corresponds to f. Okay, so if we return back, it will be var equal var ended with 0x 0f, and that is the simple notation, which is var or v. Here it is v, as I told you before. We can use var or v as a name for the variable. So var ended with equal 0x 0f instead of saying var equal var end with 0x 0f. Okay, this is the shortcut. Here, flip bits 4 and 5 in var. As you guys can remember, flipping means XORing the specific bits to 1, and the rest will be XORed with zeros. So if we return here, and actually we do this, we can actually here easily. Okay, so I want to flip bits 4 and 5. This is bit 4 and this is bit 5. Okay, so I will actually XOR, as I told you, this is the symbol of XOR. 0, 0, 1, 1, and 0, 0, 0, 0. I don't know, guys, but if someone doesn't know that the first least significant bit is bit 0 and the most significant bit is bit 7. So this is bit 4 and this is bit 5. Okay, so I'm XORing the particular bits that I want to flip with 1. Therefore, X XORed with 0 will result in here X. Here will be X. Here will be X dash, the negation. Here will be X dash, or the complement, whatever how you call it. And here we will keep them X as they are. Okay, X here and X here. So bit 4 and 5 will be flipped by XORing them with 1s and XORing the rest of the bits with zeros, just to prevent them from changing or alternating. Okay, so this will be 0x30. Why? If we go back, 0011 represents 3 and 4 zeros is 0, so it is 0x30. And we can have our simple notation, which is var XORed equal 0x30. Now we'll move to a different operations, and now we are trying to check on the bits. We are not trying to write or modify the bits. No, we want to actually isolate a bit and check its value, or exclude a bit and check its value. But actually the word isolate makes more sense. We want to isolate a bit and check its value. So check if bit 7 of var is equal 1. How can I isolate a bit? I isolate it with an AND mask. Okay, so actually I have 8 bits. Let's have an example here. It will be easier. And let me delete all of this because no longer it will be no longer needed. And here also. Okay, no, I do not want this. Okay, so actually I have our lovely 8 axes. And we'll try to actually, we want to check on bit 7, right? Yes, we want to check on bit 7. Okay, so actually I want to check on this bit to check whether it is 1 or not. Okay, so I want to make sure, or I want to do an if condition, whether bit number 7 in my var variable is actually set to 1 or not. So I need to isolate this bit from the rest of the bits. How can I isolate? Using an AND mask. And I will AND the bit I want to isolate with 1, because X ANDed with 1 will result in X. And then the rest of the bits, I will isolate them or exclude them by actually making them zeros. So I would say this is 0, 0, 0, 0, 0, 0, and 0. Because ending anything with 0 will result in a 0. Therefore, I had what? This will be X, and the remaining bits will be zeros. Okay. So now I isolated bit number 7 from the rest of the number by ending it this bit with 1 and the rest of the bits with zeros. And then I will check whether the result is equal to the mask or not. So if we go back, you'll find out that I'm going to check if V or var ended with 0x80, 1000 is 8 and 0000 is 0. So 0x80 is equal 0x80, because I want to check whether this bit number 7 is a 1 or not. So actually what did I do? I simply made the remaining bits all zeros, and then I will check whether this bit is 1 or not by actually ANDing, or by actually checking by if it is equal to actually 1 0 0 0 0 0 0 0. I want to check whether it is equal if X and 7 zeros is equal to 1 and 7 zeros or not. Because if it is equal, this means that the X is what? It is 1. If it is equal, this means that the X is 1, because I actually isolated this bit from the rest of the bits. All remaining 7 bits were zeros, and actually I'm trying to match it or check if it is equal to the mask I used or not. So if it is equal to 1 and 7 zeros, this means that bit number 7, which is this X, is actually 1. There is even a simple notation for it, which is what if var ended with 0x80, because the if condition will evaluate to false only in one condition, if all of the bits are 0. Okay, so the if condition will evaluate to false if all the bits are zeros. However, if at least one bit is a 1, not a 0, it will automatically evaluate to true. So here, if you go back, okay, if I say if my var ended with the mask and I did not actually say equal to the mask, it will perform the what? It will perform the masking operation. Okay, and we will have this as a result, X and 7 zeros. Okay, when will it evaluate to true? When will the condition evaluate to true? If this X is actually 1, because all the remaining bits are zeros. So if this bit is 0, it will evaluate to false. However, if this X bit is 1, it will evaluate to true, and therefore my condition will be succeeded or will succeed. Okay, let's move on. Check if bit number 2 of var is equal to 0. Same concept. I want to check whether this bit is actually equal 0 or not. So I will use also an AND mask. Okay, in checking, I use an AND mask and isolate the particular bit or the particular bits I'm looking for, or I want to check their values from the remaining or the rest of the bits. So here, I want to check on bit 2. Let me delete everything. Okay, and let me write, no, let's exclude. So we have here X, and 2 X's, and this is bit 3, bit 2, bit 1, and bit 0. So 0, 1, and this is bit 2. I want to check whether this bit is equal to 0 or not. Take care. Last time we checked whether bit number 7 was equal to 1 or not. Here we want to check on this bit whether it is equal to 0 or not. So I will also use an AND mask, and I will isolate all of the other bits by ANDing them to 0. However, I will AND this bit with a 1. Okay, so actually the expected result will be 0 0 0 0 0. X ended with 1 is X, 0 0. Okay, so I performed what? I performed the mask and I actually isolated this bit. Now I need to check whether this bit is actually 0 or not. What can I do? You need to guess it. And as you all guessed it correctly, pretty sure you guys are doing an amazing job, because definitely you took this tutorial on campus, so you know the solution. So what happened here? We want to check whether this bit is actually a 0 or not. So the simple solution is to actually check if it is equal to 0 or not. So I will try to check whether this mask is equal to 0 or not, as you will see in the solution here. If var ended with 0x04, because 4 zeros is 0 and 0100 is 4, so it is in hexadecimal, 0x04 is equal to 00 or not, or to 0x00 or not. As you will see, if this x is actually a 0, so when I equate it with 0x00, 0 will be equal to 0, therefore my condition will be true. There is also another solution, which is I'm going to check, instead of using equal like the previous example, I will use what? The mask itself. However, if I use the mask itself, it will be checking whether it has a 1 or not. So what? We negate the condition. So actually we have here the negation. This exclamation mark represents the negation or the complement. Okay? So I'm trying actually to what? To flip the result. If v ended with 0x04, when will this condition be true? When will v ended with 0x04 will be true? If at least one of the 8 bits is 1. Okay? So actually, if we go back here, if this x is 1, var ended with 0x04 will result in a true. However, I'm checking whether this x is 0 or not, so I need to negate it. Therefore, I put the exclamation mark, and hence the true will be flipped and will become false, because actually I want to check whether this bit is 0 or not. So saying var is ended with 0x04, it will be, this condition will be evaluated to true if this x is 1. However, I'm checking if this x is 0 or not, so I need to flip what? To flip the condition. Okay? Or you can use the easy approach of equal 0x00. Both approaches work perfectly. Check if bits 2 to 0 or 0 to 2 of var is equal 101, and here 101 is a binary number. Okay, it's not 101. This is a binary number, and take care, using a column here, 0, column 2 means I want to check bits 0, 1, and 2. It's not only bits 0 and 2. No, I'm trying here to check bits 0, 1, and 2. So I want to check if bits 0, 1, and 2 of var are equal 101. So let's go back to our sketch. We can just delete this one. Okay, and just remove the sketch. So I'm trying to check on what? On these 3 bits, bit 0, 1, and 2. So first of all, I need to isolate. Rule of thumb, first I need to isolate these bits from the rest of the bits. So I isolate using an AND mask, and I will AND all other remaining bits with 0. However, the bits that I want, I will what? I will isolate using 1s. So here x or x ended with 1 is x. Here will be another x. Okay, and the rest will be zeros. Okay, here another 0, and here another 0. Okay, so we have what? 0, 0, 0, 0, 0, 1, 1, 1, which will be, and the result will be 0, 0, 0, 0, 0, x, x, x. Now I have the result. I excluded the bits. What shall I do? I need to actually compare it. And I will compare it with what? With a binary mask. Let's be simple. I can say 0b here to represent the binary, and I can say 0b here, and I want to compare it to 0, 0, 0, 0, 0, and 1, 0, 1. Okay, here will be equal. Okay, so I'm trying to compare this value with the binary of 101. So if we go back, you'll find it like this. V ended with the mask that we used with the 3 ones at the end to actually extract the bits from 0 to 2, and I actually compared it with a binary mask of 101 for the least significant bits, and the rest is zeros, because we are dealing with 8-bit values. Now let's move on to the next question. Check if bits 5 and 4 of var is equal to 0, 1. Same exact concept, okay? We'll be doing as follows. I'll be actually just removing, no, I'll just be removing everything. Okay, so actually, if I just no longer use this, I want to check bits 4 and 5. This is 4 and this is 5, and the remaining will be X's. So I will use an AND mask, as you can see, and I will isolate by ANDing everything with 0 except the intended bits. So the result should be what? 0, 0, and double X, and the rest will be zeros. And definitely I will try to equate it with what? With a binary mask, because it's easier here to use a binary mask of 0, 0. We wanted to check with 0, 1 and 0, 0, 0, 0. Okay, so if we go back, yeah, actually here the solution used a hexa mask, but we could have used a binary mask. I mean 0x1 0. If we go back here, 0, 0, 0, 1 is actually 1, and 4 zeros is actually 0, so it is in hexadecimal 0x10. Okay, now we're done with this question. It is very important because last year in their midterm, they got around 24 marks on just manipulating bits. And a lot of students lost marks because they forgot to state the 0x and the 0b. So it is very easy to perform the bit masking or the bitwise operations. Just concentrate and convert correctly using your calculator. Question 3 in the practice assignment is the same exact or has the same exact concept as question 2. So you can guys solve it at home. I'm not going to solve it again. And you can find the solution in practice assignment 3 solution. So we have two documents on the CMS platform or the MET platform. Practice assignment 3 and practice assignment 3 solution. You can check the question from there and solve it and check the solution from the solution document. Now, the last part of the tutorial, which is the embedded C programming, which we will now move into how to write programs in embedded C. And embedded C is a very easy to program in because you use predefined libraries. Okay? So before we start, let me just give you a quick overview regarding the Atmega 328P processor or the Atmega 328P microcontroller, and what are the general purpose input output ports that are available on the microcontroller. So actually the microcontroller we are using on the Arduino Uno board, which is the Atmega 328P, it has some pins, okay, and these are input output pins. You can connect to them sensors to read data from the environment, or you can connect actuators to actually send data to the environment or to output data. These pins and ports are actually connected by some I/O registers. As I told you before, in our microcontroller, the I/O registers control the functionality of some components inside our microcontroller. The input-output pins or ports are actually controlled by 3 registers. We have the Dtr register, the DDR, we have the pin register, and we have the port register. Okay, the purpose of the Dtr register is to set the direction to input or output. So actually, I have a register which is an 8-bit register. Okay, each bit inside this register represents a physical pin on the microcontroller. If I connected a component to this pin, I need to determine whether it's a sensor, I'm going to read data from it, or it's an actuator, I'm going to output data to it. So the DDR, which is the directional register, determines whether I'm going to set a certain pin to an input pin, meaning it is connected to a sensor, or to an output pin, meaning it is connected to an actuator. And take care, if I set a bit inside the DDR register to 0, this means it is an input pin. If I set the pin, a certain bit inside the DDR register to 1, it means it is an output pin. So actually, each pin on the microcontroller corresponds to a certain bit in the DDR register, okay, in the direction register. If this bit is set to 0, it means its corresponding pin is an input pin. If this bit is set to 1, it means its corresponding pin is set to an output. So 0 means input, 1 means output. Then we have two registers. We have the pin register. This register is an 8-bit register, and each bit inside it corresponds to a physical pin. If I am actually connecting this pin to a sensor, I'm going to read the data from the pin register. So let's assume that pin 0 is the physical pin 0 maps to bit number 0 in the pin register. So if I connected a sensor to this pin, I will read its value from bit 0 from the pin register. Same goes to the port register. The port register is used to actually output data to the pin. So if I actually wrote in bit number 0 of the port register 1, the actual physical pin will output 1 to the actuator it is connected to. Okay, so pin registers to read input from sensors, port registers to output data to actuators, or to output data to the physical pin, and the pin register is to read the input from the physical pin. However, in our Atmega 328P, we have three main port categories. We have ports called the B ports or port B. We have a port called port C, and we have a port called port D. Okay, port B and D are 8-bit ports, while port C is a 7-bit port. And take care, each port here has its own DDR register, pin register, port register. Therefore, we have here the X, because the X can be either B, C, or D. So if I'm actually operating on port B, which contains 8 pins, I will be dealing with registers DDRB, pin B, and port B. If I'm dealing with the 8 pins of port D, so I will be having DDRD, pin D, and port D registers. If I'm dealing with the 7 pins of port C, so I will be dealing with DDRC, pin C, and port C. Okay, and it's really important. And we only have 3 port categories in the Atmega 328P. However, in different microcontrollers, Atmega microcontrollers, we can have port A, we can have port H, we have multiple other ports other than BCD. However, in our Arduino Uno board, which has the Atmega 328P microcontroller embedded on it, we have only 3 ports, B, C, and D. Okay, and each port has its own 3 registers, DDR, pin, and port. And each bit inside these registers correspond to one of the pins of the port. So port B, as I told you, has 8 pins on the board. Each pin corresponds to a bit in DDRB, pin B, and port B registers. Okay, you guys should have understood this from the lecture. I'm just recapping it quickly because the next question will depend on such concepts. And let's move on to the next question. And this question, we are just considering a very simple microcontroller other than the Atmega. So this is a fictional microcontroller, okay? It does not correspond to our Atmega microcontroller. I repeat, this is a fictional microcontroller. This is just a simple one for the question purposes. Because this microcontroller have 8 I/O pins related to 3 8-bit registers, one input register called the I-reg, one output register called the O-reg, and one control register called the C-reg. So it has the same concept of the Atmega. Here the I-reg corresponds to the pin register, the O-reg corresponds to the port register, and the C-reg corresponds to the DDR register. Okay, but this is a different microcontroller. The C-reg sets up the direction of each pin, whether it's an input or an output. And as you can see here, we just have one group of pins. We do not have 3 like the Atmega. And this group contains 8 I/O pins, where I can actually select or change the direction to input or output using the C-reg or the control register. If pin X is set as output, we set bit X in C-reg to 1. Its value is written on bit X in O-reg, else its value is read on bit X in I-reg. So actually, if I have pin X, I want to set this pin to an output, I set bit X in the CREG to 1. If I want it as an input, I set it to 0. Actually, if I want to read the data coming through pin X, I need to read bit X in the iReg. If I want to write data to pin X, I need to actually write data or write the data to bit X in the OReg. Initially, the CREG value is 0. And here, if it is initially 0, this means that all 8 pins are what? Are input pins. If initially the value of the CREG is 0, it means all 8 pins are what? Are set to input. Their direction is input. The question says or states, complete the following C program to control a LED from a button. Okay, so we want to actually, we have a button and we have a LED, and we want to control this LED from a button. LED is connected to pin 6 and the push button is connected to pin 5. The LED is an actuator, it's an output source connected to pin 6. The button is a sensor, it's an input source connected to pin 5. If the button is pushed, the pin will be, or it will read value 0. However, this is not the normal case, okay? Normally, if you push a button, it should read 1. However, there are special buttons, if you push them, they read 0 and they do not read 1. So this question is a special question. Pushing the button normally sets the value to 1 or reads 1 when I push a button. However, for this question, pushing a button or pressing on a button, the value will be here 0. And actually want to complete this following code. So now we need to complete this code and fill in the blanks. As you can see, the first line in the code, we are including simple micro/io.h. In embedded C, we actually need to import or include the library of our microcontroller so we can use the IO registers, for example. So for our code to understand, for example, what is port B, what is DDRC, what is SREG, I need to import for the @mega family, we include avr/io.h. However, in this fictional microcontroller, we are including simple micro/io.h so we can use the namings of our IO registers like iReg, CREG, and OReg. And here at the beginning, our code definitely will be in the main method or the main function. And in C, the return type is int, and at the end we return 0, which means that we've executed our main function correctly. We want here to set the CREG bit number 6 to an output. Okay. Why do we want to set bit number 6 as an output? Because our LED is connected to bit number 6. So I need to set this bit as an output. And our button is connected to what? If we go back, our button is connected to pin 5. However, initially, the control register initial value is all zeros, and 0 means input. So I do not need to rewrite 0 to the register, because actually what happens, it is initially as an input. So pin 5 is initially input. However, pin 6 is initially input, and we need to transfer it or change it to an output by writing 1 to bit number 6, so the LED we can control the LED. And actually, how can we do so? If I go to my sketcher or sketch, and I delete all of this, this is the reason we taught you bitwise operations and bit masking, because we are going to use it now. Initially, I know that all values are 0. Okay, initially, the CREG, if I do like this, initially, the CREG, all 8 values inside it are zeros, which means they are what? Input. I want to set bit number 6, which is this bit, to output. So I need to write 1. How can I write 1 using AND or OR? I will use OR. Because ORing anything with 1 will result in a 1. And ORing anything with 0 will remain as it is. So 0, 1, 0, 0, which will result in 4 in hexadecimal. 0, 1, 0, 0 is 4. And here we'll keep them zeros. So what shall I do here? I am doing CREG ORed with 0x40. I can actually write it here. CREG is equal to what? Is or equal to 0x04, which is equivalent to CREG equal CREG ORed with 0x04. or it is equivalent actually to CREG, or equal 0B 0100 0000. Okay, all of these are correct representations. Now I set bit number 6 as an output so I can control the length. Let's go back to our question. While 1, because as I told you, we are dealing with real-time embedded systems, okay? And real-time embedded systems must actually sense the environment continuously. So they are in an infinite loop, because if it is not in an infinite loop, it will only work once. However, we are dealing with embedded systems that must be working 24/7, that must be sensing the environment 24/7, or always sensing the environment. Therefore, it is on an infinite loop, and hence while 1 or while true. Now we have here an if condition, and we want to check if the button is pressed or no. If you remember that here we have a special case that if we press the button value will be, or the input value will be 0. Normally it should be 1. However, in this question, it is specified that when I press or push a button, the input value should be 0. And the button is connected to pin 5. So we need to read actually the value of pin 5. From which register? The CREG, the IREG, or the OREG? Definitely the IREG, the input register. Okay, so if we go back to our sketcher, let's just delete or hide this. And actually, let's just, I cannot operate on it. Okay, yeah, I can now operate. So actually, I do not know the values of the IREG. I mean, the IREG will have values access. This is the IREG, the input register that I will read the input of the button. Okay, I can write it here. This is the IREG. Okay, when I push a button, its value will be written here. And since it is connected to pin 5, this is bit number 5. So actually, we need to isolate. Remember, if I want to check, I need to isolate this bit from the rest using what? Using an AND mask. And definitely I will isolate with 0, 0. I want this bit, so I will put 1, and here 0, and the rest will be zeros. Okay, and then here I will have what? 0, 0, x, 0, 0, 0, 0, and 0. So actually I wanted to isolate bit number 5 from the remaining bits, or the rest of the bits. So what did I do? I performed an AND mask. I cleared all the other bits, and I ANDed my intended bit number 5 with 1, so I can have its value. Now I need to what? I need to compare. Okay, I can compare it equal. If the button is pressed, it means what? That x should be 0. So I can actually compare it with 0b and zeros, or actually it would be easier to write 0x 0 0. Okay, or I actually can negate the mask, but just let's do it simple. I will try to actually, the IREG ended with, will be 0x02, because 0010 is 2 and 0000 is 0, so it will be 0x20. IREG ended with 0x20. Is it equal to 0 decimal, or 0b80 binary, or 0x00 hexadecimal? Now we want to turn the LED on, and to turn the LED on, I need to send a high signal. Sending a high signal meaning setting it to 1, and the LED is connected to pin number 6. Therefore, if I go back here and I actually delete everything, which register will I operate on? If I set the direction using the control register, CREG, I read an input from the input register IREG, so I will be sending my data to the OREG, which is the output register, which is equivalent in the @mega direction. The CREG is equivalent to the DDR, the IREG is equivalent to the pin, and the OREG is equivalent to the port register. So actually, we have here what? We have here the OREG, and I do not know the OREG value. and I do not want to actually affect or mess up with the other bits. So the ORAG is XX, XX, and here for other X's. I want to actually turn it on. So I need to send a high signal. I need to set bit 6 to 1. So I need to what? To OR. If I want to write 1, I need to OR. If I want to write 0, I need to AND. So it will be ORed with 0, 1, because we are actually interested in setting this bit to 1, and the rest will be zeros. So I'm not affecting the rest of the bits. Okay, here it will be what? It will be X, 1, and the remaining will be X's. Okay, so we can actually say that ORAG is ORed equal with what? If we 0, 1, 0, 0 is 4, and 4 zeros is 0, so 0x40. Or we can say ORAG equal ORAG ORed with 0x40. Or 0b1 0100 0000. Okay, this is how to turn on the LED. Actually, if you go to our code, you'll find out that we have an else part, meaning that, well, if actually the condition is false, I need to what? I need to turn off the LED. Turning off the LED means we need to actually clear bit number 6 in the ORAG. And to clear bit number 6 in the ORAG, clearing means what? We need to AND it. So we need to have an AND mask. So instead of using an OR, I need to do what? I need to actually AND, and I'm interested in bit 6. So everything I will AND with 1 here, and 0, and 1, and 1, and then 1, 1, 1, and 1. Okay, so anything ANDed with 1 will result in itself. Anything ANDed with 0 will be clear, it will be 0, and we'll be having X and X, and the rest will be X's. Okay, so I actually cleared bit number 6, meaning I turned the bit the LED off. If I want to write it, for example, let's do the binary. Let's do it in binary. So it will be ORAG ANDed equal this time with 0b10111111. Okay, this is an approach just to tell you how to write in binary. Okay, also we had a different approach. We could have actually taken the previous mask, which was 0x40, and negated it, because actually negating the previous mask will result in this mask. So let me get, so 1 0 1 1 1 1 1 1 is the negation of what? Of 0 1 0 0 0 0 0 0. So we could have used the negation, and you'll find out that the solution actually negated it. So as I told you, first we set the direction of the LED as an output by writing 1 in the CREG on bit number 6. However, the button is already initially initialized as an input because initially the CREG was all zeros. Here we checked on pin number 5 because it is the input pin from the iReg where the button is connected to. We checked if it is 0 or not. If it is 0, I'm turning on the LED by sending a 1 or setting bit 6 to 1 in the OREG. Otherwise, if I want to turn off the LED, I'm going to set this bit to 0. Whether you create a mask from scratch or you just negate the previous mask and use an AND. Okay? Now our last question, why can't we eliminate the else part in the code? It is simple, because the LED wouldn't turn off if we stopped pushing the button. I mean, if I pushed the button and kept pushing, what will happen? I want the LED to turn on. However, if I actually removed my finger from the button, I want the LED to turn off. If I did not have an else part in the code, the LED would have not been turned off, or it will remain on, and actually I want the LED to turn off. Okay, so instead of just keeping the LED on for the first time, if I pressed the button and I did not have an else part in my code, the LED will continue turning on or be on forever. However, if I have an else part, if I remove my finger from the button, so I do not press and I remove my finger, the LED will turn off because there is an else part which actually clears bit number 6, and clearing bit number 6 in the ORAG will result that the LED will turn low, or I'm sending a low signal, so the LED will be turned off. Okay, because so I can actually alternate between turning on and off, instead of if I only clicked on the first time, it will always remain off, it will always remain on if I did not have an else part. So now I'm done. I hope you guys enjoyed the tutorial. If you have any questions, you can just post it on Piazza, or you can send us an email. Hope you guys are actually surviving the semester. Stay safe, good luck, and see you next time.